A toy gun inventor may have built the engine that makes steam look old. Not a better turbine, not a cleaner boiler, not a smaller piston. An engine with no pistons, no spinning blades, and no mechanical motion doing the work. It takes heat that factories, vehicles, power plants, data centers, and abandoned wells normally throw away, then turns it straight into electricity. The strange part is, the heat does not even need to be extreme. Temperatures around 100 to 200 degrees Celsius, or 200 to 400 degrees Fahrenheit, may be enough. That is too weak for many steam systems, but not useless to this machine. Its inventor is Dr. Lonnie Johnson, a nuclear engineer who also created the Super Soaker. And his new machine may attack one of energy's biggest leaks, heat we already paid for. Burn fuel, move a vehicle, bake cement, cool a server farm, or run a turbine, and heat escapes into the air. It rises from exhaust stacks, radiates from metal, and vanishes into cooling systems. Industry uses roughly 1/3 of all energy on Earth. In some processes, up to half of that energy leaves as unwanted heat. That is not a small leak. That is a river of power flowing past machines. Here's the trap. Much of that heat is low temperature. It is hot enough to injure, boil, or burn, but not hot enough to drive classic steam equipment efficiently. That changes everything. Dr. Johnson's machine is called the Johnson Thermoelectric Chemical Converter, or JTEC. It is still in commercial development, but its promise is brutally simple. Turn low-grade heat into electricity without moving parts. That promise puts it directly against one of the oldest patterns in power.
Heat water, make steam, push a turbine, spin a generator, extract electricity. It works, but every step adds losses, friction, maintenance, and complexity. Steam is powerful. Steam is also needy. JTEC takes a different road. It does not burn fuel to make heat. It looks for heat that already exists, industrial exhaust, geothermal warmth, or hot gases from engines. Then it converts that temperature difference into electric current.
No rotor, no blade, just heat, pressure, hydrogen, and a membrane. The working material is hydrogen gas. But hydrogen is not burned, consumed, or used as fuel. It moves through the system, gives up electrons, takes them back, and returns to its starting form. The same hydrogen can repeat the cycle. The key component is a proton exchange membrane. Think of it as a gate with extremely strict rules. Hydrogen gas reaches one side under heat and pressure. At the membrane, it separates into protons and electrons. The protons pass through the membrane. The electrons cannot. They are forced around an external circuit instead. That detour is electricity. On the other side, the protons and electrons reunite, forming hydrogen gas again. The molecule is rebuilt after lending its electrons to the circuit. The trick is not destroying hydrogen. The trick is making hydrogen temporarily power a load. Heat provides the push. As gas warms, pressure rises. In one example, hydrogen can move from about 100 pounds per square inch toward a region near 0.01 pounds per square inch. That pressure drop drives the hot side reaction. But the cycle is not finished. The hydrogen must return to the hot, high-pressure side. A second membrane helps reverse the process on the cooler side. The hot side produces more voltage than the cold side consumes, leaving electricity available. That difference is the prize. The story behind JTEC begins long before advanced membranes and energy investors. Lonnie Johnson was building machines before most people had touched a computer. In high school, around 1968, he built a robot named Linux. It was powered by compressed air. It used jukebox switches for control. Its memory came from a reel-to-reel tape recorder. At the time, robots were mostly television fantasy. Johnson tried to make one real. He later trained as a mechanical and nuclear engineer. His career took him to Oak Ridge National Laboratory in Tennessee, the Air Force Weapons Laboratory, and NASA's Jet Propulsion Laboratory in California. He worked on the Galileo and Cassini missions. That resume would satisfy most engineers. Johnson kept inventing at home. One project involved a refrigeration system using water instead of ozone-damaging CFCs. During that work, he machined a nozzle and watched it blast water across a bathroom with surprising force. A side experiment became a billion-dollar toy. The first Super Soaker prototype used an empty soda bottle, PVC pipe, nylon tubing, and homemade valves. Its pump compressed air, and that compressed air fired a powerful stream of water. The design changed water guns in the 1990s. More than $1 billion worth of Super Soakers have been sold. Johnson used his share to fund deeper, harder inventions, including JTEC. A toy helped finance an energy machine. That is the twist. Johnson first conceived JTEC in 2003. The idea arrived before some required materials were ready. For years, the concept existed ahead of manufacturing reality. Then in 2020, he gathered engineers at JTEC Energy in Atlanta, Georgia, to push it toward hardware. The machine now has interest from major energy players. One investor came from oil and gas, looking for a way to convert low-temperature heat in abandoned oil wells into electricity. The claim is startling. About 20% of abandoned oil wells in the United States could supply all U.S. power needs. That is not a better battery. That is not a new fuel. That is buried heat. The reason JTEC matters is efficiency. Waste heat only becomes valuable if the conversion system is affordable and effective. If the device costs too much or converts too little, the heat keeps escaping. In 2020, a laboratory version of JTEC reached 17.1% thermal efficiency, using a heat source at 200 degrees Celsius or about 400 degrees Fahrenheit. At that temperature, that result was nearly half of Carnot efficiency. Carnot is the theoretical ceiling for any heat engine operating between two temperatures. Nothing can beat it. Engineers can only approach it. That makes percentage of Carnot a serious measuring stick. Common low-temperature heat-to-electricity systems often reach about 12% to 13% efficiency at similar temperatures. That is roughly one-third of the Carnot limit. Johnson's goal is about two-thirds of Carnot, and his team says test data points toward that possibility. That would be enormous. JTEC can also run backward, and the same electrochemical principles can move heat the other way. In that mode, it becomes a cooling or refrigeration system. A heat engine that can reverse into a cooler is not just clever, it is commercially dangerous to older machines. But physics is only half the battle. The membrane must survive pressure, heat, cycling, and manufacturing costs. At high temperatures, around 500 to 600 degrees Celsius, JTEC uses ceramic membranes. At lower temperatures, such as industrial waste heat or geothermal sources, it uses thin, flexible membranes held between support layers. Those membranes must restrain pressurized hydrogen. Higher pressure improves performance, but it also raises mechanical demands. A small sheet must behave like a precise chemical gate and a pressure vessel at the same time. That is not easy. Johnson has said the system could be competitive with other options in about 5 years. He has also projected that in 10 years, it could become the lowest cost energy system in the world. That is bold, and bold claims invite brutal engineering tests. Scaling is the hard part. Waste heat is messy. It does not always arrive as a clean, steady stream. Some factories run batch processes. Some exhaust contains chemicals that must be filtered. Some heat spreads across metal surfaces instead of flowing through a neat pipe. Capturing 20% to 50% of lost industrial heat may require custom hardware at each site. A cement kiln is not a data center. A bakery is not a steel mill. An abandoned oil well is not a gas turbine exhaust stack. Heat is everywhere. Useful heat is picky. JTEC Energy is targeting 250 kilowatt units, a size that can compete with generators. The first commercial unit is being built for a major utility company in the southeastern United States. Initial markets are expected to include waste heat from existing engines, especially turbines and gas turbines. That strategy makes sense. Many natural gas power plants already use hot exhaust in a second cycle to squeeze out more electricity. JTEC could add another layer, harvesting cooler leftover heat after conventional systems are done. One fuel burn, more output. So, did the super soaker inventor kill the steam engine? Not yet. Steam will not disappear overnight. JTEC still has to prove cost, durability, manufacturing scale, and field performance outside the lab. But the threat is real. The physics works. A lab device reached 17.1% efficiency at 200 degrees Celsius. The design has no moving mechanical core. It can use heat that many systems ignore. It can also reverse into refrigeration. The unanswered question is whether membranes can become cheap, rugged, and scalable enough for industrial deployment. If that happens, JTEC would not replace every turbine. It would attack the wasted heat below them. That is the real disruption. Not a giant power plant replacing the grid overnight. Not one miracle box ending every energy problem. But thousands of silent converters bolted onto the places where energy already leaks away. Factories, wells, engines, data centers, turbines. The world already produces the heat. The world already pays for the heat. Then the world throws it away. The lesson is simple. The next energy breakthrough may not come from finding a new source. It may come from refusing to waste the sources we already have. Johnson has pursued this idea for almost a quarter century. A simple water blaster could be built from bottles and pipe. This machine demanded new materials, patient engineering, and years of pressure. And that makes the contradiction sharper. The inventor famous for turning air pressure into play is now trying to turn industrial pressure into power. The engine is quiet. The next engine may not roar. It may not spin. It may separate hydrogen in silence, while the old world wastes heat into the sky.